be a 50 bar. He took.
You ever wondered how high a human could actually jump if we pushed our bodies to the absolute limit? Humans have been fascinated with flight for thousands of years, from the story of Icarus to Leonardo da Vinci's ornithopters and to the Wright brothers' first airplane. We've always wanted to leave the ground and stay there. But what about doing it with nothing except our own bodies? Today, I'm looking at the question, what is the maximum jump height a trained athlete could theoretically reach before the human body's durability becomes the limiting factor? To investigate this, I'll be using concepts from our physics class, including Newton's laws of motion, force, acceleration, and projectile motion. For this investigation, I'm using professional dunker and jumper Darius Clark as a reference point. He's about 6 feet 2 inches tall and weighs approximately 200 pounds, or around 90 kilograms. He is currently the person in the world with the highest vertical jump of 51 inches. To keep things simple, I'm making a few assumptions. First, I'm assuming that the takeoff time of the jump is about 0.2 seconds, which is roughly average for elite jumpers. Second, I'll ignore air resistance, because it will only slightly reduce the height and hang time while making the calculations much more complicated. And finally, I'll use estimated durability limits for some important body structures involved in jumping. The Achilles tendon at about 3,500 newtons, the patellar tendon at about 5,000 newtons, and the tibia at about 11,000 newtons. These values will help determine when the body starts becoming the limiting factor. The first thing I want to figure out was the relationship between jump height and hang time. Using the equation for projectile motion, I found that total hang time can be related directly to jump height. After simplifying the equations, I ended up with h equals 122.5 times the time squared, where h is the jump in height, in centimeters, sorry. Using this equation, I calculated a few benchmark jumps. A jump with 1 second of hang time corresponds to about 48 inches, or 2 feet. 1.5 seconds is about 108 inches. A 2-second hang time would be impossible, as it would require a jump height of over 16 feet. Of course, knowing the height isn't enough. The next step is figuring out how much force would be needed to actually launch a person that high. To do this, I used Newton's second law, force equals mass times acceleration. First, I calculated the takeoff velocity required for each jump height. Then, I used the takeoff time of 0.2 to calculate the acceleration. Finally, multiplying acceleration by body mass gives me the force required for takeoff. The results were interesting. A jump height with 1 second of hang time, or about 48 inches, required roughly 3,000 newtons of force. A jump height with 1.2 seconds of hang time, or about 69 inches, required about 3,500 newtons of force. And a jump height with a 2-second hang time would require 5,200 newtons. Now here comes the interesting part. How do these compare to the durability limits of the human body? When I compared the required forces to the estimated breaking strengths of the Achilles tendon, the knee one, and the tibia, a pattern emerged. At around 3,537 newtons, which is roughly 69 inches, the Achilles tendon would reach its estimated breaking point. That means if an athlete could somehow generate the force necessary to jump higher, their Achilles tendon would likely fail before they could safely do so. The knee tendon survives much longer. Its estimated limit isn't reached until about 5,100 newtons compared to a jumping height, corresponding to a jumping height of roughly 13 feet. And then the tibia never becomes a limiting factor until you get to like 300 inches. It's a non-factor. Now, what does this mean? Based on the calculations, the Achilles tendon appears to be one of the first major structural limits. It suggests that the theoretical maximum height is for a jump is about 69 inches, or about 5 feet and 9 inches in feet and injuries. Before injury becomes a high probability. That's actually not too far away from what athletes have shown that they can produce. Olympic sprinters have been can generate forces of around 3,500 newtons with each step, which is very close to the force needed for that 69-inch jump. Nobody, and will likely not see a person jump that high in a long time. However, there's nothing directly stopping them, at least according to the physics, that's stopping some exceptional athlete from doing it in the future. In conclusion, using all of the methods used, I found that the Achilles tendon is the first thing to become a limiting factor, one of the first things to become a limiting factor, and that the theoretical maximum jump height is about 69 inches, or about 5 feet 9 inches, with a hang time of approximately 1.2 seconds before your body starts becoming the limiting factor. Of course, real life is more complicated than physics on paper. Factors like muscle efficiency, fatigue, technique, and injury prevention all play important roles, but based purely on the physics, it seems that the human body may be much closer to reaching its jumping limit than most people realize. Thanks for watching.